So we'll try to see some ordering between these various modes that we talked about through the idea of cutoff frequencies, right? So I told you that the Pythagorean relation for the components of the propagation vector can be written this way, right? So k1 of course is omega square root of mu1 epsilon 1, okay. So we said that kx is equal to m pi by a and ky was n pi by b, right. So we can say that kz, right, which is the phase constant for a given mode mn, right, is given by square root of k1 squared minus m pi by a whole square minus n pi by b the whole square. Okay. So in order for us to have a propagating wave, right, this kz has to be real, right, which means to say that the terms that are subtracting, right, which is kx square plus ky squared, better be less than k1 squared, right, or the term underneath the square root has to be greater than 0, right. That is the condition for having a propagating mode, right. So when I look at the equality is when I can look at the, so omega c squared mu 1 epsilon 1 is equal to m pi by a whole square plus n pi by b whole square. Okay, this just implies that my cutoff frequency for a mode index m comma n is given by 1 over square root of mu 1 epsilon 1 right. So it is clear that the cutoff frequency is actually dependent on the indices m and n, right. And this doesn't seem to have a bearing on whether it is TE or TM, right. So we can say that this is for both TE Mn or TM Mn, right. Of course, for the TE case and the TM case, there are certain restrictions on whether m or n can be 0, right. So the allowed values for m and n for the TE and the TM case might be slightly different, but nonetheless, given a valid index m comma n for a particular class, right, whether it is TE or TM, the cutoff frequency is given by the same expression, right. All right. So let us try to picture this, right. So let us look at the frequency axis. So this is my 0 hertz, okay, and to the right is increasing frequency, right. So we said that for TE the lowest index order that we can have is 1 0, right, and that would have the lowest cutoff frequency. This is because we have assumed that the longer dimension is along x, right. So between a and b we have this relation that a is greater than b, which means that m pi by a would be a smaller number, right, than n pi by b if m and n were the same, right. So if I were to compare between TE10 and TE01, right, m being 1 and n being 0 will give rise to a smaller cutoff frequency, right. So in this scenario where I have assumed A is greater than B, right, the first cutoff that we would see is for that of the ordering 1 comma 0, and you would call this the TE10 mode, right. Higher to this would be the TE01. Okay, so you can say that this is the cutoff frequency for the ordered pair 0 1, and then whether it is for TE11 or TM11, we will have the same cutoff frequency for the ordered pair 1 comma 1. Okay. For higher indices, you may have to know exactly what A and B are, right. For example, if A was greater than 2B, right, you will notice that the TE20 mode, right, might actually have a cutoff frequency that is lower, okay, than that of TE01. Again, just refreshing our memory, what does the cutoff frequency mean? It is a high pass device, which means that I can have electromagnetic waves propagating through this waveguide higher than the cutoff frequencies, right, which is to say that the range from 0 to Fc, there can be no propagating modes. Okay, and there is very special region of operation between the first cutoff frequency and the second cutoff frequency. We call this single mode operation. So frequency okay. So the range of frequencies demarcated between the TE10 and TE01 would be the range of frequencies where the waveguide will only support one mode, right. This is a very special region. Most people try to build waveguides such that for the frequency of interest, they would like to keep the waveguide single mode, right, that they would not like to have many modes operating within the waveguide. This just keeps the design and the construction of the circuits simple. Okay. So the very first mode with the lowest cutoff frequency also has a special name. It is called the fundamental mode of the waveguide. Okay. The mode with the lowest cutoff frequency is also called the fundamental mode of the waveguide, and all the other modes are often lumped into something we call higher order modes, right. So we can finish this thought. The F cutoff for TE20 could be less than the F cutoff for TE01, right. In the case that the dimension A is much larger than even 2B, we can find that the cutoff for even TE20 could fall below that for TE01. Okay. So you can just implement this in the expression for the cutoff frequency, and you can verify it for yourself. Okay. All right. So I believe we have looked at what is a mode, right? And then we tried to learn as much as we could in terms of constructing solutions or picturing the fields, beginning with the parallel plate waveguide, and then we looked at the rectangular waveguide, and we noticed that some key ideas and concepts such as cutoff frequencies, right, and mode classifications, and also what is the propagation phase constant, and ideas of phase velocity and group velocity, right. So with this I will wrap up the course on rectangular waveguides and waveguides in general. So in this day and age, we no longer evaluate the mode field patterns, right, the vector field patterns, using pen on paper calculations, right. The rectangular geometry lend itself to solvable expressions for electric and magnetic fields, but for more complex geometries, people usually use commercial softwares, right. So today, the company ANSYS is able to provide a free version of their software, especially for students, right. So the ANSYS electronics desktop student version is available for free for students to understand basic concepts in electromagnetics, such as waveguides and antennas and so on. So I was able to pick this up in less than a week, right. And there are even YouTube videos explaining how to set up the waveguide geometries within their software and evaluate mode field patterns for different modes that are supported within the waveguide, right. So I will provide some links in the description. I highly encourage students to visit these links, one of which is the ANSYS video that explains how to make this waveguide that I am showing here. It is one where the horizontal dimension of the waveguide is 22.86 millimeters and the vertical dimension is 10.16 millimeters, and you're looking at the field pattern for when the excitation frequency is 17 gigahertz and the rectangular waveguide is filled with air, right. So with click of buttons today, the software is able to provide the solutions to electric and magnetic fields. I also want to provide one more link, right, one more YouTube link, which actually links to another faculty from IIT Madras who has given an excellent series of lectures on the same topic, but he actually uses the software Octave in order to simulate live with the students on how to generate the field patterns, right. So you don't have to think that this is not something that you could do from scratch, right. And indeed the instructor provides very simple and elegant codes to visualize electromagnetic fields for some simple waveguide geometries using some software that you could readily get access to, right. So it is not that you will always have to go with a commercial software. If you know the background on how to go about implementing Maxwell's equations, right, in a numerical form by discretizing time and spatial dimensions, you yourself can also get the field patterns yourself, right. So please go through those links and perhaps that could inspire you to get more into this field, right. But here I am just going to show you the fundamental mode of this particular rectangular waveguide. I am showing you three cross sections. So this is the electric field intensity. So it is not quite showing you the direction in which the electric field is oriented. The color just indicates that red being a very large electric field intensity and blue being near zero intensity, right. So you can see that close to the walls, one pair of walls, the electric field intensity is very close to zero, right. For a perfect conductor, right outside the boundary, it is zero. But the software does not stop there. It certainly allows you to visualize the field patterns in various cut planes, right? So we looked at the face. Certainly these provide us a glimpse, right? Because it's a 4-dimensional object, right? The electric field, because each point in space has a direction and a magnitude that needs to be represented. So one can best show you only cross sections, right, to interpret how the fields look like within the waveguide, right? And this is a picture that is trying to show that for the fundamental mode, the electric field, right, is basically top down, right? So these little cones, the red cones, indicate the direction in which the electric field is pointing, and of course the color of these cones indicate the strength of the electric field, right? So I would essentially have high field intensity close to the center of the waveguide, right? So if you can remember the half cycle picture that we drew for the parallel plate waveguide, where the field intensity was maximum at the center, that's the same thing that you're noticing in this image, right? So as I gradually move to the sides near the walls, the field strength diminishes, although always pointing in the y direction, right? So remember that this is our y, x and z, right? For the TE10 mode, which is the fundamental mode of the rectangular waveguide, the electric field is pointing in the y direction, right, all throughout the waveguide, right? There's no other component. Remember, the TE mode does not have a component in the propagation direction, so Ez is 0, but Ex is also 0. We can quickly verify that. So if we put in the value for m equals 1 and n equals 0, we notice that Ex becomes 0, whereas Ey has some value to it, right, and also some functional dependence. It is cosine of n pi y by b. Sorry, n is 0, right? So cosine of n pi y by b would be 1. Sine of m pi x by a, where m equals 1, becomes sine of pi x by a, which is the half cycle that we drew. So one more thing that I would like to show is, I would like to show you how a rectangular waveguide looks in practice, right? So this is a rectangular waveguide where you can see the cross section is a rectangle, right? The dimensions are so chosen that it is about single mode at 10 gigahertz, right? So this is a waveguide used for 10 gigahertz electromagnetic fields, right? And it is a single mode at this frequency, and you can see that the construction is essentially a good conducting metal, right, from all four sides, and you basically have these protrusions on the end, which are the faces of your waveguide, right? You can see little protruding bits of metal, we call them flanges, so that I can combine this waveguide element with other components and structures, right? So one can, in this domain of rectangular waveguides, construct objects like filters, splitters, combiners, and so on, and you can attach these segments one after the other by really designing them with flanges, bringing them in close proximity and bolting them right together. For example, I have one more rectangular waveguide based structure. This is called a horn antenna, right? You can see that it has a similar flange with an entry port that matches the exit of, say, this waveguide, right? And on the other side we have a flare moving out to a much larger dimension. We call this a horn antenna. So this is a waveguiding element on one side, and I can attach it to this waveguide at this flange using bolts, right? So I have little holes in these four corners, and I can use screws and nuts to essentially affix different waveguiding elements like this in order to construct a large scale microwave circuit. Okay. So now that we have discussed about all these concepts leading up to the waveguides, I believe that we will try to wrap up the course next week by looking at all of these, the transmission lines and rectangular waveguides, in the context of building a microwave frequency network, right, and looking at S parameters, and finish the course with that. Okay, thank you.